In this video, I'm going to show the image of why you still need a PAM4 SerDes, even though the circuit image is more complicated than the NRZ SerDes. There are lots of motivational images you can think of, such as remote learning, remote office, social media, AI, cloud computing, data streaming, online business, online shopping, delivery system, self-driving, etc. Therefore, higher throughput demand comes from the areas of data center, storage, automotive, high-definition video, high-definition media, e-commerce, high-performance computing, HPC, 5G wireless, IoT, etc. If you must go to a higher throughput, what are the challenging images you have? Think about your own images for 5 seconds. Correct. The first challenge of a higher throughput would be the speed. To meet the high-density data transmission in the data center, HPC, or switching and routing, we could increase the speed, but the SerDes system performance would degrade, especially if the transmission data rate is greater than 50 gigabit per second. First, the transmission channel would be much worse at higher frequency, and we will discuss the images in detail later. Secondly, the on-chip device process spread or variation would be greater at higher frequency, since the operating frequency would be close to its limit. Lastly, higher frequency operation will lead to more aging concern and lower lifetime of the SerDes due to its electromigration and self-heating inside the device and metal routings. What else could be the higher throughput challenging image? Bingo, cost. If we need to replace all the infrastructures due to the higher throughput requirement, the upgrade cost will be enormous. In addition, the cost might not be proportional effectively. For example, 20% performance improvement might need 2x cost, or 100% performance improvement might need 10x cost. Therefore, we like to reuse the existing infrastructures without any cost at the channels such as the cable or connectors. But how could we double the data throughput without upgrading the infrastructures? Right. If every 2 bits NRZ data is encoded into a 4 multi-level PAM4 data stream, then the data bandwidth is the same. Your data transmission image here shows the maximum data transition of both NRZ and PAM4 signals is 1 UI. But the throughput images show there are 8 bits NRZ data in the channel, while there are 16 bits PAM4 data in the channel. Again, the images show the PAM4 can double the data throughput, but keep the data bandwidth without upgrading the infrastructures such as the cable. Let's look at the channel images of the PAM4 versus NRZ. For channel loss of a PAM4 versus NRZ SerDes evaluation, we could check their insertion loss at Fn for PAM4 and the insertion loss at 2 times of Fn for NRZ. Assuming the circuit noise and other conditions are similar in both PAM4 and NRZ. If the insertion loss difference delta IL is greater than 9.5 dB, then the PAM4 is a better choice. Otherwise, the NRZ would be preferable. But why? Think about your system images for 5 seconds. As we discussed in the Why NRZ SerDes video, the PAM4 signal power is less than the NRZ signal power by 9.5 dB, and the RX equations are to compensate for the channel loss within the next frequencies. In other words, we must compare the I high after the X equalization, which is the VEQ. If the channel insertion difference delta IL between NRZ and PAM4 is greater than the 9.5 dB, then apply maximum swing 1 volt at both PAM4 and NRZ before the channel. The X output I high of the PAM4 could be greater than output of the I high of the NRZ, even though the I high of the PAM4 is ideally 1/3 of the NRZ. So, the channel loss image shows you that we should consider insertion loss difference at Fn and trace Fn for a decision between PAM4 and NRZ. Please be advised that only the channel loss and signal power were considered in the evaluation, but other metrics such as power, complexity, and area were ignored for ballpark evaluation. After understanding why you need the PAM4 SerDes, let's look at the PAM4 SerDes technology images you may have. The simple technology would be the aggregate-based SerDes with the low power property, but the PAM4 circuit impairments are much worse over PVT and require lots of digital calibrations and adaptation algorithms. To achieve a strong adaptability and a good performance after precise calibration, the DSP-based SerDes is necessary in PAM4 at the cost of a much higher power. For example, the DSP-based 56 gigabit per second PAM4 SerDes could consume more than 1 watt in 28 nanometer with major digital power. Owing to the device technology improvement, lost digital power can be reduced greatly, or the speed can be increased a lot. Here is a summarized image for why you need the PAM4 SerDes. The main reason is the demand for high data throughput. Either the bandwidth reduction or cost down can mitigate the challenge of high throughput from the high bandwidth requirement. To have a reliable PAM4 SerDes, the extra power is necessary for a DSP-based technology, which may conflict with your previous low power and low complexity circuit images. Lastly, the DSP-based PAM4 has been well implemented into 112 gigabit per second SerDes in the industrial, and you can find lots of products in several applications we mentioned. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with people who may benefit from it.